I'm Bartek Lipinski, and I'm an Android tech lead at Fabulous. And today I would like to be speaking to you about generating Kotlin extension functions, and especially doing that for the purpose of improving annotation processing. Okay, so if you want to follow along with the slides, they should be up there. You should be able to download them right away and go on with the slides as I go on as well. So let's do a quick introduction, like a super shallow, short introduction to annotation processing. Most annotation processing libraries have two components, or at least two components. The first one is annotations. It's a super lightweight thing that can easily be included in your code base, and it's basically a set of labels or a label for marking the particular part of your code. And that's something super lightweight, so you could put it in your code base without bloating your APK size. And the second thing is a compiler, which can be much more heavy, because we are not really limited by not introducing that to our code base. In fact, it should never be introduced in your code base. If it is, actually, there's something probably wrong with either how the developer of the library developed the compiler, or in the way that you introduce the compiler in your code base. Its main job is to find the uses of those annotations within your code base and doing something with them. It can do many different things, but code generation is actually, I think, the most interesting one. Few things about code generation that you have to remember are the limitations of it, or the different things that it makes it very particular. For example, and the most important thing, is that annotation processors can never modify existing code. They can only generate new code. And you have to remember that understand that very soon, if you're trying to write an annotation processing library, because you really have to change the way you think about annotation processing. Apart from that, you have to remember that code that is generated by the compiler is generated in compile time. So when you're writing your code, the generated code will be available later on in the process. It's not available for you right off the bat. The fact that you can refer to the generated code from your IDE is because the IDE is doing some funky business with giving you codes from the previous rounds of compilation. And the last thing it may seem a bit redundant or unnecessary, but the generated code is actually unknown until it's actually generated. Those three facts raise two important questions from the perspective of a user of the library. The first two raise the question of what code will actually be generated, and the third thing creates a question of when will it be generated. And all those three things, you can come up with a simple conclusion from all those three things, that it's very difficult to refer to generated code. It's very difficult to actually use the generated code. And that's the problem that many developers were trying to tackle. And in fact, most of developers that were trying to come up with a solution for this problem ended up with using one of the two approaches that I found. The first approach is something I like to call the I don't care approach, and the second thing is the reflection bridge approach. Let's talk about the first one first. So how many of you have ever used Dagger? Of course, okay. So for any of you who haven't, that's a dependency injection framework, and it actually generates a lot of code, like a ton of code. If you ever wonder how much, just go through the code, or even throw an exception within the provision method or something. You will see a stack trace of hundreds of methods. And the entry point to this ton of code is actually, in basic setup, one class. The class that implements your component. And Dagger expects you to use a class with the name of your component prefixed with the word Dagger. How many of you have seen something similar to this? So the fact that the IDE is not able to resolve Dagger app component. That's like a typical thing you see when you're first trying to use the Dagger. And that's the reason for that is that until the first generation of the code, This Dagger app component class is unknown, and the IDE cannot hand you over this. So you can only hope that Dagger will give you this in compile time, but it will give you this only if everything goes correctly. If anything goes incorrectly within your component setup or module setup, or even if you make a typo within any of those two, this code will not work. So that's the main problem with this approach. It's basically saying that something will be generated, and you have to trust the library that it will generate the code, and you have to use it like this, without even knowing if the code is correct or not. So the I don't care approach is very easy to implement but only for the developer. It's not straightforward for the user of the library, because it highly depends on documentation. Let's do the simple thought experiment. Just imagine that you didn't know anything about Dagger, like anything at all. And I hand you over this library, and I tell you to figure it out without any documentation. Do you think you would be able to resolve that you have to use this class of your component prefixed with the word Dagger? I don't think so. You really have to read the documentation to figure out what's going on. Because this approach puts the responsibility for the proper usage of the library on the user of the library and not on the developer of the library. The second approach that I would like to speak to you about is the reflection bridge approach. And I'd say it's quite sophisticated. And when I first started analyzing it, it was actually, I was impressed, the least to say. Because apart from having the annotations component, it actually provides a different component, a runtime library. And within this runtime library, so something that you can include in your project, and don't worry about it as well, because it's lightweight, quite lightweight. Within this library component, there's something that I like to call the reflection bridge. And this little component within this library knows something about how compiler works. And having this knowledge, the runtime library, so something that you can refer right off the bat, right after you include it in your project, this library can actually find the generated code in runtime. The only downside of all this is the fact that it does that with Java reflection, hence the name of the reflection bridge. So how many of you have heard of a library called Butterknife? Probably most. Okay, so it reduces Android boilerplate, of course, for views, resources, etc. It generates, for every single class that you use, some of those Butterknife annotations inside, it generates a class with underscore view binding suffix. And you can access those classes using a set of methods, a set of bind methods of the class Butterknife. So how does this reflection bridge work? So what does it know, really? Basically, this is an example of this generated class from Butterknife. And the reflection bridge knows few things. First of all, it knows the pattern of the name of the class. So it basically knows that if you added an annotation within the main activity, it will create a class with main activity underscore view binding. It also knows that this class will be put inside a particular package, to be exact, the package where your main activity sits in. And of course, it also knows the API of the generated class in the form of an interface, basically. So the reflection bridge, having this knowledge, the reflection bridge can find generated classes, can create instances of them, and can return those instances in the form of an unbinder interface. Very simple, yet very sophisticated solution. This approach is actually very straightforward. If you make the same thought experiment as before, if I hand you over this library, you probably would be able to figure out how it works. Because it puts the responsibility for the proper usage on the developer of the library and not on the user of the library. The only downside is that it depends on Java reflection, which has some performance overhead. Even if it's not that big, it has some performance overhead. So those were the two approaches that are currently in use. I would like to propose the third approach, something I call the extension bridge approach. The extension bridge approach from the outside looks very similar to the reflection bridge because it also has the runtime library, which you can include in your code and you can use it right away. But instead of the reflection bridge approach, instead of the reflection bridge, it has something I call extension bridge end cap. Why end cap? Because it just pretends to be the real thing. It just acts as a point that you can refer to right after you add this into your library, but it does not really do the thing that you want to do, because the thing that you want to do will do the extension bridge core, which will be generated as a second thing in the compile time, and it will kind of attach to the runtime library, giving you a transparent solution for referring to the generated code, because this part knows how the compiler works. And this will be also done in runtime, but without Java reflection. I will speak about this a bit more later on. So why do I want to call it extension bridge? Of course, because of Kotlin extension functions. So why do I want to use Kotlin extension functions? Because they seemingly add behavior to existing classes without modifying them. And if you think about that, you can, for example, add a method to a string class, which is final and closed, and you cannot modify it. And you can actually, where the string is the receiver type, so the string will receive this extension functions, basically. So you can actually call this method like it was a member, this function as it was the member function of the string itself. And if you remember the third slide of mine, the annotation processors cannot modify existing code. They can only generate new code. So this actually fits very well with the whole extension function concept, because you can make it look like you're modifying the code, but you're actually adding new code. You're just adding new extension functions. To prove this concept of mine works, I created two libraries for the two libraries that I mentioned before, one for Dagger and one for Butterknife. And I would like to, first of all, speak about the Butterknife to explain the concept even more. So there are two things that you really have to think about when thinking about this concept. First of all, the end cap, so the thing that is shipped as a library. You can refer to it right after you include it in your project. No need for code generation. That's just a simple extension function on a, let's say, artificial object, but don't worry about it right now. And if you look at the parameter of the extension function, it's very non-specific. It's just activity, like a base class for us, for this purpose. And if you look at the contents of this class, it just throws an exception. It just pretends to be the real thing. It's not giving you the real class. But it doesn't matter, because the real class will be handed over in the generated extension function. And if you look at the name of the function, it's exactly the same, but the target, the parameter, is much more specific. So having this setup, having those two extension functions in your code base, if you pass the main activity instance as the parameter of those two methods, the Kotlin compiler will choose the one that is generated and not with the one that is just pretending to be the real thing. And if you look at the contents of it, the first one is just throwing an exception, and the second one is actually giving you the class that is generated by the Butterknife. And it's doing it without any Java reflection. It knows the name of the method, just like the Butterknife reflection bridge did. It knows how to create it, and it knows how to return it as an unbinder interface. All this originally was achieved with Java reflection, but here we are simply creating classes. So that's how the end cap looks like. What the end cap looks like. You've got a set of bind methods that represent the same thing that the bind methods from Butterknife do. And you've got this artificial object declaration, a singleton, which becomes the receiver type of bind methods. Why did I decide to do it like this? Because I wanted to maintain the same way of calling the Butterknife code. Because this is the way you would do it with the original library. And if you want to use the extension function method for it, you would just do it like this. Not a big difference. So let's do a quick demo to show you how it actually works. Okay, so here I've got like a super simple demo activity. Let me just clean the project right off the bat so you will be able to see it when there's nothing generated. The normal butter knife call would be just butterknife.bind of this, right? But if you look at the butterknife KTX bind, the extension function that I was talking about, with the cleaned project, you can go inside and you will see that it leads to the end cap. So it leads to the method that is just throwing an exception. Let me just build right now because I think it will take a while. So you can see that all those methods right here are just the thing that I was mentioning before. That the end cap is just a set of methods with the object declaration of a new kind. If I go back to the simple demo activity, now that the project has been built, if I do the same thing and I go to the bind method, now you will see that after building the project, it leads to the proper implementation of the extension function. And you can see that here it's just creating the view binding, the instance of the view binding class. If we go to the butter knife, well, let's actually compare those two things. If you go to the butter knife, you will see that the first line is exactly the same. It's just obtaining a source view from the target activity. But the second line, here we are just creating an object, but here it's hidden behind the create binding method. If I go inside, here's where all the Java reflection thing is going on. Okay, let's go back to the presentation. And I've done the exactly same thing for Dagger too. I've created an artificial object declaration, Dagger, and I've created a dummy, a stub implementation of an extension function that pretends to be the real thing, but is just a bit more complex because it takes generics into place. The generics are being used here. And it just throws an exception, and you can call it right after you include this in your library. And when the build succeeds, you can actually refer to a different kind of extension function that really creates the instance of Dagger app component. And this is generated on demand, and the one that is throwing an exception is just treated as a library. And having this setup, you can forget about calling the create on unresolved Dagger app component, because you can call dagger.create of app component right after you include that in your library, in your project. So how do you do it? Well, of course, you are using a library from Square. That's like probably a default answer to many questions in Android development. You should actually use Kotlin Poet. I actually will not go into too much details of how do you generate extension functions, because it's very case-by-case thing. But you can actually see one example of them, of the extension function being generated. It takes a name of the class, of course. It's a bind. It's a bind method. It takes a return class, which is here an unbinder. The most important thing is that it takes also a receiver type, and that makes it an extension function. If you didn't specify the receiver type, the Kotlin Poet will just generate a member function, basically. You add a parameter. Here, the target class name has to be more specific than the target from the end cap. That's how it actually works. And of course, we add a statement that is the real implementation of the extension function. So to summarize, this approach is much more straightforward, because it's actually as straightforward as the reflection bridge approach, because it also puts the responsibility of the proper usage on the developer of the library and not on the user of the library. And the last thing is that it does not use Java reflection, almost. Because I would like to show you some more demos of this. First of all, let's look at the demo that I call static resolution. Here you can see that we've got a static resolution activity, which just extends an activity. And it has one annotation from Butterknife here. Let's go to the correct resolution. If I pass by the way, the project is built. It's the same project that was here before. If I pass the static resolution activity parameter, so the instance of a static resolution activity as the static resolution activity, not as a parent of it, I will just end up in the correct extension function, the correct implementation of the extension function. But if I try to cast it to the parent activity, I will end up in the end cap, even though the code is generated. And that's exactly what Chet was talking about a moment ago. It's because the extension functions are resolved statically. So basically, the extension function become static. You can think of it this way: that extension function become a static function in Java, in JVM with the receiver type being the first argument. It's not undergoing the normal inheritance cycle. So if in this case it would just work incorrectly, even though we've got correct code being generated. And the second thing about that is the Java interoperability. So as I said, you can refer to extension functions from Java, but they just become static functions with the receiver type as the first object, as the first parameter. So if I go there and I try receiver is butter knife instance, you will actually see that even though the code is generated, you've got the proper extension functions being generated. If I go inside of it, I will still end up in the end cap of the extension bridge. Why? I'm actually not that sure, but I think that because this is a Java file and not Kotlin file, the Kotlin compiler does not take part into resolving the Kotlin extension function. I'm not sure if that's the case, so even if you know something more than that, feel free to let me know. Those two things that I mentioned are the main reasons why you should go for something like a hybrid extension bridge approach. So basically, do the exact same thing that I did before, so that we can find the code in runtime, but use the Java reflection inside the end cap. So basically, instead of throwing the exception in the end cap, you should just end up having a fallback solution that you just pass the target inside the original butter knife bind method. And that way, if everything goes correctly and you end up referring to the extension function that was generated, you will be just creating the view binding class normally without any performance overhead. But if something goes incorrectly, or for example, you have only access to the activity class, to the parent class of the activity and not to the eventual instance of the activity, you will just end up using the Java reflection approach. So that will be it. Thank you very much for listening.